Is
it working? Okay.
So let me introduce Giuseppe Savaré from Bocconi University in Milan, who will talk about dissipative evolution of probability measures. Thank you.
Okay, so thank you very much for the invitation and the possibility to present these results in collaboration with Giulia Cavagnari and Giacomo Sodini about first tentative to define the evolution of probability measures driven by sort of suitably adapted notion of dissipative probability vector field. So I will briefly discuss the setting and the problem, then I will make some analogy with the theory of contraction semigroups in Hilbert spaces, and then I will present the main results of our investigation. So, as I mentioned, the problem is to study the generation of evolution semigroups driven by dissipative probability vector fields. So, the setting is standard. E is a finite dimensional Euclidean space or an Hilbert space with infinite dimension. P2 of E are just a set of probability measure with finite quadratic moment. I will denote by this symbol the push forward of a given probability measure, and gamma given mu and nu probability measure in two spaces. Gamma mu nu is just a set of couplings. So probability measure in the product spaces whose first marginal is mu and second marginal is nu. And when you have mu and nu probability measure with finite quadratic moment in the main space E, you may introduce the standard Wasserstein 2 distance, minimizing this quantity among all couplings with marginals mu and nu. And gamma 0 or gamma O are the set of all the optimal couplings between mu and nu. Okay, what is probability? What is the most general definition, a possible definition of probability vector field? I will denote by TE the tangent space, which is trivially isomorphic to the product space of E and E, but it is useful to use this notation. The first variable is the position, the second variable represents a velocity, and so X and V will also denote the projection on the first two variables. So a probability vector field can be represented by a general map, perhaps multivalued, defining some domain in the space of probability measure P2E with values in P2 of the tangent space. So it will be a joint probability measure in space and velocity, such that for every element in F mu, the first marginal of F is mu itself. So you may disintegrate this in order to understand the interpretation. You may disintegrate this F with respect to the first marginal, and you get a family of probability measures indexed by the X position, which represent probability laws on directions or velocity starting from X. In the standard case, regular case, f of x maybe is concentrated on a single vector. And therefore, instead of using this complicated measure distribution, you can use a vector field f, which depends on the position and on the whole distribution of points parameterized by mu. So it's a mapping from E and P2 of E into E. But in the general case, we can allow for a general probability measure parameterized by X. So you see here in the picture, in the regular case, if you start from a distribution, a discrete measure mu concentrated in 3 points, x1, x2, x3, in the regular case, you have just vectors in x1, x2, x3, whose direction depends on the position and on the joint measure mu. In the completely general case, you have at every point x1, x2, x3, you have a distribution of velocity, which is fx1, fx2, and fx3. So it's a probability measure in the space of velocity. And so in this way, you can also consider more general measure mu, which are diffuse, and to every point of the support of mu, you may think that you have a distribution on the velocity space. And the idea is to try to define an evolution of probability measure driven by such a general F. Formally is a sort of differential equation in the space of measures. And just to, we have various levels of generalities. In the classical finite dimensional regular case where F is just a vector field depending on X and mu, perhaps one of the most recent and general results are provided by the recent paper by Bonnet and Frankowska, differential inclusions in Wasserstein spaces. You have as an example, a vector field which is the sum of a vector field depending on the position and a sort of convolution of a vector field where all the distribution mu enters. And when you want to characterize the solution, you have a continuity, the classical continuity equation, where the velocity vector v is for every time t is exactly characterized by the vector field f. But of course, you may consider a more general situation. One is precisely the associated to a gradient flow. You start with a general lambda geodesically convex or just geodesically convex function in the space of probability measures, and f perhaps is a non-smooth functional like the one I'm reporting here, so is a sum of a potential interaction and a more general energy. And so in this case, the vector field minus f is the so-called multivalued Wasserstein subdifferential of the energy. I will come back to this, to the precise definition later on. And even more generally, if you move from subdifferentials to arbitrary probability distribution, this notion has been introduced by Piccoli in finite dimension with a different approach with respect to the one I'm presenting here. But the idea is exactly to give a general map from measures to distribution of velocity, whose first marginal is the measure itself. Okay, and one typical application could be a perturbation of a subgradient, which is not a subgradient itself, so it is not generated by a function. Okay, so in order to understand what are the reasonable assumptions and what one can expect of from this theory, it is useful to have in mind what happens for points in Hilbert space, evolution in Hilbert spaces. So in Hilbert spaces, just to focus on contraction evolution, they are related to dissipative operators. So a dissipative operator is just a map such that for every x and y, if v is in bx, w is in by, you have the dissipation relation through the vector, to the scalar product of the Hilbert spaces. And this property has a natural metric interpretation. If you start from x and y and you move in the direction of your vector field, you can compute the derivative of the square distance along this motion, and you see that the derivative of the square distance is precisely the scalar product entering in the dissipation inequality. And therefore, the interpretation of dissipativity is just that, let's say that the the perturbation driven by the vector field B do not increase asymptotically the distance at time tau equals 0. Okay, so you have this interpretation. So the distance of the perturbation is bounded by the distance at the initial time 0 plus a small little o of the step tau. And it is interesting that in Hilbert spaces, you have also a corresponding notion of resolvent. So instead of moving in the direction of the field, perhaps you start from x and y and you solve this equation, implicit equation in x prime and y prime. And you can prove that if you are able to solve them, the distance between x prime and y prime is bounded by the distance between x and y. This is x prime and y prime are just the resolvent, so identity minus tau b, the inverse of this map. And a nice characterization of dissipativity is that this resolvent map is a contraction. And there is this general characterization of maximally dissipative operators. They are precisely the operators for which you are always able to invert identity minus tau b. So the resolvent is defined in all the space H. And so you have that for every x, you have a unique solution y, which is j tau of x. And it's interesting that when B is the subgradient of a convex function, this resolvent coincides precisely in this variational minimization problem, where you have a perturbation of the distance square and the function. Fine, and so since you have, when you want to solve the equation driven by B, you have two methods. In finite dimension, the most familiar one is perhaps the explicit Euler. So at each step, you solve this equation, which is very simple, since you start from x n minus 1 tau, and you just add the tau plus b x n minus 1 tau. So at each step, you have a nice application of the operator to the previous step. But if B is dissipative, you can also consider the implicit Euler method, where you see that the main difference is that at each step, on the right-hand side, you have the operator computed in x and tau instead of x n minus 1 tau. So you have to apply at each step the resolvent instead of the operator. And in any case, both for the explicit or the implicit Euler method, if you are able to apply them, then you can construct a sequence given a step size tau. Then you can consider the piecewise interpolant of such a sequence, and you end up with a family of discrete solution. When tau goes to 0, you may hope that this family of discrete solution converge to a limit. And there is this celebrated Kandad-Liggett result showing that if you have a dissipative operator and you solve the implicit Euler method, then the Euler scheme converges uniformly to a limit curve with a nice and precise error estimate of order square root of tau. And this limit curve can, of course, solve the differential equation generated by the operator B if the curve is Lipschitz. In the general case, it is the unique integral solution of this family of differential inequalities in the distributional sense, which are formally obtained by computing the derivative of the distance from an arbitrary point, fixed point y, using the differential equation, using the dissipativity condition, and ending up with this inequality. Okay, so this is precisely this is the best situation. So we have maximally dissipative operator, we apply the implicit Euler method, the implicit Euler will converge, and the limit is characterized by this nice variational formulation. What happens if we come back to the set of measures? Of course, the explicit extrapolation is easier, since at every measure mu, we can select, so the role in the Hilbert space of the increment x plus tau b of x now is played by this expression. We have at every measure mu an element f whose first marginal is so a probability distribution in the space E Cartesian E. So we can apply the map x plus tau v to this probability distribution, and you find this family f bar tau, which is a family of probability measures in P2 of E, depending on the step size tau. This is this is the obvious generalization to measures of what you are doing for in Hilbert spaces for the explicit Euler method. For instance, just to understand it, if x and v is, if you can represent f by the push forward of every probability measure p by these two maps, x and v, then this evolution curve is just a push forward of the same probability p by the map x plus tau v. Okay. So, what is the main difference with the probability with the Hilbert setting? The point is that when you compute the distance square, as we did in the case of the Hilbert setting, so the distance square along this family of perturbed measure, the effect is that the Wasserstein distance is no more convex and nor lambda convex for any lambda. In fact, it is a semi-concave function with respect to the parameter tau. This is an important point, since differently from the case of the Hilbert space, if you compute the right derivative and the left derivative, so the left derivative of this distance square is larger than the time derivative, the right derivative, and in particular, it does not satisfy the inequality you need for obtaining the contraction property of the resolvent. And a very simple example, if you start from two distribution, mu0 in blue and mu1 in red in R2, and you move them along this direction, vertical direction, so this is the direction of your vector field F applied to mu0, and you compute the distance square from a reference measure nu in green, then you see that at some point there is this the optimal map connecting mu t with nu switch in this simple way due to the symmetry. And if you compute the graph of the distance square, you see here a plot which is not convex for every positive lambda, parameter lambda. So it is a semi-concave function. So also the left and right derivative, for instance, at time 1/2 may have a jump discontinuity in the wrong direction. So in order to characterize the metric dissipativity, the standard way is to compute the right derivative of this quantity. So we perturb any measure mu along the direction f, we fix a reference nu, and we compute the right derivative at time tau equals 0 of this quantity. This can be done, and this could be a sort of surrogate of the scalar product of the velocity along the direction joining x and y, since in Hilbert space this time derivative is precisely what you use to compute the scalar product. And what you get, you introduce a coupling between f and the nu. So this is obtained by choosing 3 random variables, xv parameterizing f and y parameterizing nu, with the constraint that the push forward of x and y is an optimal coupling between mu and nu. And then the right derivative of the Wasserstein distance along this perturbation generated by the field f from nu is the minimum of the expectation of this scalar product, where again x, v, and y generates a coupling between f and nu, which is optimal in the marginal x and y. Of course, there are many possible coupling of this type, and then you have to take the one realizing the minimum expectation, the minimum integral. It is interesting to observe that the left derivative has the same expression, but then you have to take the maximum expectation. So the left derivative is maybe strictly larger than the right derivative. To define dissipativity, you proceed as in the Hilbert space. In the Hilbert space, you computed the right derivative of the perturbation starting from 2 points, mu and nu, along a selection of your vector field. You compute this derivative, and you observe that this derivative in general is larger than the derivative of these 2 quantities we have defined before. This is precisely the right object to define dissipativity. So a general probability vector field is dissipative if for every mu and nu in P2 of E, for every selection of f and in mu and in nu, this metric scalar product we defined precisely here satisfies this right inequality, so is a sort of general definition of dissipativity. Okay, so it is interesting that this is consistent with the case of subdifferential of convex functionals. So if you have the Wasserstein subdifferential, it is dissipative according to this definition, and vice versa. If the differential of a functional is dissipative, then the functional is geodesically convex. And okay, I will skip this part. What is the main difference with the case of subgradient is that for subgradient, you have a simple way to define the implicit scheme by using the JKO minimizing movement approach and minimizing at each step this functional. In the general case, you don't have this variational approach, so the implicit scheme is not clear how can you implement it. Okay, this is one of the main difficulty. The second difficulty is that even if you are able to implement the implicit scheme, since the distance square is not semi-convex, it is semi-concave, dissipativity does not imply contraction. So it is not at all clear how to use even if you are able to define the implicit Euler method, it's not clear how to use it. And so you have also to manage this fact that F, the vector field, can split particles. And of course, you have also to use optimal displacement interpolation, since dissipativity is related to this kind of optimizing coupling between measures. Okay, so what is the simple idea that due to this fact, we started to think about the explicit Euler method. The explicit Euler method, of course, can be defined more easily if the only constraint is that you have to assume that at every step, the explicit Euler method will keep you in the domain of the operator in order to apply it in a recursive way. And of course, the second important a priori assumption that we make is that along a solution given by the explicit Euler scheme, we are able to control the Lipschitz velocity of your curve, the Wasserstein velocity, which in fact is the quadratic moment of your vector field with respect to the velocity vector. So starting from mu0 with a step size tau, a Lipschitz bound of the velocity and the final time t, we will denote by this symbol the set of all the discrete solution of the explicit Euler method starting from mu0 up to the final time t, satisfying a uniform bound of the velocity. And the main result is that assuming that you have a dissipative vector field, assuming that you have a discrete vanishing sequence of step sizes going to 0, and mu k is a solution of a discrete solution of the explicit Euler scheme starting from mu0 with these step sizes and satisfying the uniform bound of the velocity L up to time t, then you can prove that this solution is converging uniformly in 0t. It will converge to a unique curve independent of the step size and on the selection you do in the vector field. Moreover, your limit solution is a Lipschitz curve, and it is the unique solution of a dissipative AVI, which is modeled exactly as a Benillan solution in Hilbert spaces. So you may define it by taking the the distributional derivative with respect to a given test element nu, and on the right hand side you have the surrogate of the scalar product between the vector field f at nu and your evolving measure nu. And finally, you have also an optimal error estimate, which is a part of the precise size of the constant C, which is exactly as the Crandall-Liggett estimate for in Hilbert spaces. C is of order 10, more or less. So it is explicit, not so nice, but explicit. And it is a universal constant. And moreover, this is, just to conclude, this is just an example of application of this setting. Suppose that you start from a general dissipative probability vector field such that it is defined on all the measure with bounded support in your space. And suppose that if you fix a measure with bounded support, there exists a small radius rho and a constant L depending on mu0, such that in a neighborhood of mu0, your probability vector field is concentrated on measure with bounded support given by this L size. And moreover, suppose that in general your probability vector field is concentrated in a set of position and velocity such that the scalar product between velocity and position grows like x squared, constant x squared when x goes to infinity for some constant c not depending on f. This is the typical growth that you have for monotone dissipative operator in Hilbert spaces. Then you can prove that you can generate a semi-group of contraction. Every curve precisely is characterized by the EVI inequality, and you have the classical contraction property of your evolution by using, in this case, the explicit Euler method. I will skip other characterization and just conclude with the extensions and possible future developments. Everything can be easily extended to lambda dissipative probability vector fields, so it is not really necessary that you are contracting. Also, you can deal with the evolution which are exponentially satisfy some condition like W2 mu t nu t less than exponential lambda t distance between mu 0 and nu 0. We think that in dimension, if the dimension of your space is larger than or equal to 2, then this kind of evolution will not split particles. In dimension 1, there is a simple counterexample due to Piccoli, and this could be, of course, what remains interesting to study is some extension of the implicit Euler scheme, and to use this a priori estimate to derive, for instance, stability and G convergence of this evolution. Okay, so thank you for your attention. I'm stopping here.
So thank you, Giuseppe. And maybe we have time for just one question because we are a bit over time. A question from the audience or from the Zoom audience?
Hi, thanks a lot for the talk. Can you hear me? Yes, I think so. All right. Actually, very naive, just general question. Like, you were saying that you have this, the classical example of this setting is when you have subgraders of the function. Do you have some other example outside this class which was sort of interest to you to study this problem, or it was mostly about perturbations of subgradients?
You can, in general, you can, if you have, like the case of potential energy, if you have, for instance, you can construct interaction fields by using not subgradients but general monotone maps. And so, for instance, take a subgradient plus a monotone map which is not a gradient, or directly an operator which is still the integration of monotone but not subgradient map. These are cases, examples, say. But I think that you may construct a much more general example. Say that I presented the case of dissipative since it's easier, but if you include lambda dissipative vector fields, then every reasonable measure valued vector field which depends in a locally Lipschitz way from your data, this satisfies the dissipative, lambda dissipative property. So the range of application should be quite large.
Thank you.
You're welcome.
Thank again, Giuseppe and Mr. Leonardo. And so the coffee break is outside, and we'll resume in 20 minutes, I think. Where is yes, in roughly 20 minutes. Okay. And so if I don't know if you had other questions for Giuseppe and Leonardo, if they maybe stay a bit longer, so that if someone has a question, you know, like posing questions in the coffee break, but it's difficult to, you know.
I have a quick question. Sorry, I have it.